Welcome, everyone, to a Clear Mountain interview with Professor Bogdan Staszewski. Professor Bogdan, it's so good to have you. Thank you. A brief introduction. Professor R. Bogdan Staszewski is a leading researcher at University College Dublin, where he works on making wireless communication, the Internet of Things, and even quantum computing more efficient and practical. Bogdan has co-authored 6 books, over 350 publications, and holds more than 200 US patents. Previously at Texas Instruments and Delft University of Technology, he has co-founded several startups, including Equal One Labs, which is building the first single-chip quantum computer. And we first heard about Professor Bogdan through a presentation he gave at Dharma Realm Buddhist University on the intersection between quantum and Buddhism, and where so often you hear these two kind of spoken about by those who don't know much about quantum. The fact that you, Professor, actually have deep insight into kind of the ins and outs of quantum meant that your thoughts on that intersection actually had gravity, and really appreciate you taking the time.
Thank you very much for inviting me.
Well, so maybe we could just begin. Could you give us a bit of just talking briefly about your path to working with quantum computing and your path to becoming interested in its convergence with Buddhism?
Okay, so I'm not a quantum physicist. My full education from undergraduate, graduate, and PhD was electrical engineering. I studied a little bit of quantum as necessary for understanding semiconductor devices, because nowadays these elements, these devices, transistors, if you will, in CMOS semiconductor technologies are becoming so small, they are nanometer size, that we are dealing with individual electrons. So we observe a uniquely quantum effects such as tunneling, for example, right? Superposition, tunneling, and when you turn on your computer, your processor, your computer, about 1/3 of power consumption when you don't do anything, and the idle power is because of tunneling, basically, which is a quantum effect. It's not classical effect, but it's a quantum effect, right? You don't see tunneling in real world. So we study this at a very unsophisticated level, just to understand, being able to understand these issues. But then around 2017, so I basically spent 20 years in Texas Instruments in Dallas, Texas. Then I moved to Netherlands, to TU Delft, Technical University Delft, to start a group in digital RF in microelectronics. Then after 5 years, I moved to Dublin, which I'm still here. And we were working on some early versions of quantum computing, qubits, single electron transistors in TI, just as a hobby, trying to break into this new wave of cell phones. Our goal was to build a quantum computer on the cell phone, but of course that was a goal for decades, but we couldn't do it simply because the process technology was good enough, and it requires too much money, so we decided not to continue. But then around 2018, I got back with my former friends from TI, and we decided, hey, now it's the right time to start digging in quantum computers. But the problem was we wanted to use the technology due to Moore's law of scaling, because Moore's law of scaling basically says that every 2 years, the gate density, the transistor density will double. Right, and the cost for incremental cost of individual transistor will go down by half. So it's like exponential scaling. So And this Moore's law of scaling has been on for decades, several decades, and with a mathematical precision nearly, it has increased and decreased the cost, increased complexity of CMOS semiconductor technology to such an unbelievable level where now you have AI, basically. You have billions of transistors, hundreds of billions of transistors able to do some very sophisticated things that kind of mimic neurons, what's going on in human brain, and give answers which many people get fooled thinking that this is intelligence, right? This is not real intelligence, but thinking. So basically, when we start diving into this, we discovered, hey, there's so much to learn about quantum mechanics. So I had to brush up my old books, get some new books on quantum mechanics, and basically read it. And when I was going through, lots of things didn't make sense. Like, for example, superposition. Right, then particle can be in both places at the same time. Can be in point A and B at the same time. It's not that you don't know, but it's indeed in two places. And then you can take these two places, separate them to the end of the galaxies, or on the opposite side of the galaxies, and this is just one particle in both places. And when you observe one part, the other part gets collapsed. So, for example, if you observe spin of an electron, it's up, and the other one will be down. So that's a principle of superposition. We don't have any equivalent of this in the classical world. Like, the only thing I can think of is some religious stories of Father Pio, for example, from southern Italy. People reported him being in both places at the same time. So it's a little bit kind of a humorous example, but this is the closest I can think of in that I can relate to people not knowledgeable about the quantum mechanics. So then superposition, then entanglement, that the particles are entangled, and you can separate the long distance, and then when you do some observation on one, the other one changes instantaneously without abiding by the speed of light constraints, right? So that's when Einstein never accepted this. He was against all these interpretations of quantum mechanics, Copenhagen so-called interpretation, because it violated his findings of general relativity, for example, right? So we were learning all of this. So things didn't make sense, but then I started thinking, well, wait a minute. In order to explain why quantum mechanics works and why it could be so powerful, because all chemistry is quantum, basically, right? All chemistry is quantum, 100%. Nuclear bombs, nuclear energy is quantum, right? 100%. A majority of the semiconductor devices are quantum. You need to understand quantum effects to build CMOS devices, semiconductor devices, IC chips, right? So they are ingrained part of our life. But we don't know how to interpret it. So we can make engineers and scientists can make a lot of money building these quantum devices. Now, lots of effort. Many countries in the world are spending tons of money, billions of dollars on building quantum computer. Right, that's the new race, scientific race and technological race. But nobody understands why quantum computer works. Right. So I was thinking about this, and surprisingly, a very clear answer was coming from Buddhism. That Buddhism was actually explaining lots of these things in different language, coach in different language, right, in different words. But knowing Buddhism, having a dive into quantum mechanics, I was able to connect these two things and say there is this uncanny compatibility between the two. So to me, I'm a student of quantum mechanics, right? Because I'm engineer, electrical engineer by electronic engineer by profession, I'm diving into quantum mechanics, and I use Buddhism to explain, to understand why quantum mechanics works. Right? It's not that the physics of quantum mechanics that doesn't work. So Schrödinger equation basically describes everything at the quantum level, right? And it's been used over and over again, millions of times, to explain all the phenomena. Right? It does work, right? There has been no example contradicting Schrödinger equation. But the only problem, we don't know the interpretation of Schrödinger equation, right? There are different interpretations, and none of them really make sense, to be honest, right? So I'm using Buddhism to try to understand why. How can we make sense out of this new field of science?
Hmm. Yeah, you've mentioned a couple of terms which I think could be useful to draw out a bit, just in terms of looking at, in Theravada Buddhism or in all Buddhism, we've got these three characteristics of impermanence, uh, unsatisfactoriness, and not self. And three
Mhm,
terms which you mentioned are tunneling and superposition and entanglement. And one other term is quantization. I'm
mhm.
curious if you could draw out those four principles just to show how what we see, like I'm looking at a computer and I'm looking at Ajahn Nisabho, whereas tunneling, photons are these very small quantum, these very, very tiny particles, the physics of the very, very tiny world don't operate in the same way that our perceptions do. So curious specifically around anatta or not self, and specifically around how so much of our perception of self and others are based on just what we see, like the person here, and how these four principles of tunneling, quantization, superposition, and entanglement actually really mess up those perceptions, and maybe defining those for people as well.
Well, so I don't look at these specific characteristics of quantum worlds, such as tunneling, superposition, entanglement, as kind of one-to-one related to anatta, dukkha, anicca, right? So the characteristic of being that you mentioned, but I look at them as composite to indicate that there is impermanence, right? Anicca, there is impermanence. So the problem with the most of the religions is that they take the concept of permanent self, right? And Buddha was struggling with this. Atta or Atman in Sanskrit, right? So that is a cornerstone of Hinduism. Well, there was no Hinduism at that time, but Brahminism, the current religion at the time of Buddha. So he was against it, and he introduced the concept of anatta, which is no self, which basically says that self is not a substance but a process. So he didn't deny the self, right? He didn't say. He said many times, "Oh, monks, you need to exert yourself in order to reach nibbana," right? If he denied self, he would never say that, right? So what he denied was the permanent self, which is some substance being there. And physics, obviously, even classical physics cannot find self, cannot find that substance. But obviously, classical physics cannot go very deep at the subatomic level. So quantum physicists look into this and say, okay, at the lowest depth of dimensions, there is no permanent self, right? So that permanent self doesn't exist. But the contemporary science agrees with the life as a stream, right? As a process, that things depend on another one. So I don't think there is. If you take a very serious discussion nowadays with science and Buddhism, I don't think there will be disagreement that self exists, but self exists as a process, basically, at a given moment of time, right? So what quantum physics, brings into this is that how do you define time? So according to the recent discoveries of quantum physics, time doesn't exist. Time is just an artificial construct, right? So there is a present moment, there is a previous moment, there is a past, which is previous moments, future are something to come. And the past doesn't exist. Where is the past? Right? Past doesn't exist. When you look at all the physics equations, the time is bidirectional. The time doesn't have the constraint of a single direction. That time has to go from past to the future. There is no such there is no such constraint, right? All the physics equation, Newtonian equations, Schrodinger equations, right? Time is just a variable, right? It doesn't say it has to go from a negative number to positive number, right? Present doesn't exist. Right? Well, future doesn't exist because it hasn't come yet. Present is so momentary, such a short duration of time, that by the time you realize it, it's already gone. Right? So you might say present is ephemeral, right? Doesn't exist. So physics brings into this supports the theory of momentariness, that only the very instantaneous moment exists, and it just disappears. And once it disappears, the past doesn't exist. And the latest developments also suggest that time doesn't exist. Time is just emergent property. So Newton was very strong. He used time, he considered time as one of the absolute principles, that time is the same everywhere, time is universe. Einstein, with his special relativity, says, no, time is just depending on the speed of the observer, right? So depending on how fast you go, you can slow down the time. But that was kind of incremental contribution to the science, but the general relativity basically completely turned this view of time on its head. Basically, it says that time is depends on gravity. There is no absolute time. There is no universal time. Time might appear relevant to a specific point in space, right? So if you're somewhere else, your notion of time is different. And not only that, it also depends on the speed. So basically, time is some mathematical variable which doesn't really exist. And there are some new theories which basically says that the reality is rather five-dimensional or more dimensional, and time is just a projection of going from fifth dimension to fourth dimensions, basically. So time happens like that, and because of this projection, the time goes into one direction. But this hasn't been proven yet. These are some serious theories that physicists are discussing, and we are going to see further developments into this. So when you take and look at this from physicist perspective, there is not much disagreement with the Buddha said, right? I mean, at the same time, Buddha basically said what does he thinks what people need to know in order to practice, in order to realize that there is a suffering, impermanence, and so on, without really giving the full prescription, because Buddha was a physicist, right? So didn't want to go into details and overwhelmed his audience with details which they were not ready for, right? So had he, this is just a speculation, had he lived in the age of quantum mechanics, where mathematics was so well developed, he probably would have used Schrodinger equations to basically describe the impermanence and egolessness, and maybe even dukkha.
One of the key insights that I took away from your presentation was just a pretty powerful rejoinder to the idea that consciousness is just an emergent quality of the brain, and the observer effect and collapse of the wave function, really pointing up consciousness as a pretty primary element of the universe. And I wondered if I could share a few slides you put together on the two-slit experiment and the Wheeler's delayed choice experiment, just to kind of flesh out that observer effect a little bit, and kind of also just break down people's conception of how clear Newtonian, like how strange the universe is, basically.
Mm-hmm.
I have that here. Can you see it, Professor?
Mm-hmm.
Yeah, so would you tell me when to move slides, but if you'd walk us through the two-slit experiment, double-slit experiment, and then the Wheeler's delayed choice experiment, that could be really
Yes,
great.
this is a classical experiment, basically to show that Newton was wrong, right? So Newton was right about his law of motion, gravity, right? So he basically has a great contribution to the development of science, scientific method of inquiry, and so on. But there were some statements that he did that were very very clearly explained, but not really proven, right? So Newton said that vision, sight, is corpuscular, right? That you have particles from the sun. They are beaming to different objects. They are reflecting from objects, right? You're looking, for example, at a house, right? Reflecting from the house, and they impinge on your retina, right? So this is what he did. So these are particles. Young did this experiment in 1801 to basically disprove Newton. Say that he was wrong. He wanted to show that light is actually a wave, not a particle, corpuscular object, but light. So what he did on the left, on the very left, he did this experiment where there was a beam of light. You can think of like if you have a flashlight. There was probably not flashlight, but there was some equivalent in the past, right? So there is this beam of light. It goes and hits the obstacle, and the obstacle has two holes, right? S1 and S2. Right? Can you point out to these holes S1 and S2, right? And when it hits, it generates, it goes through, so the wave cannot go through, but the part of it will go through, but it will create waves. It's like you put a finger or you throw a stone into a lake, into water, right? So it generates its own waves. So if you make one wave, that's fine. It's difficult to observe, but if you make two of these slits, then they will propagate towards the screen on the right, and they will create so-called interference pattern, right? That the energy will or amplitude will add up constructively or destructively, right? If it is constructively, you will see high amplitude. If it is destructively, you will get zero. So you see this pattern. So the explanation why they add up constructively or destructively is on the top right. So you have waves, right? They have a certain wavelength called lambda, Greek letter lambda, wavelength, right? And then when you add them at the screen, combined with the screen, in the first example, they just have opposite amplitude, so they destroy each other, right? So amplitude will be zero. And on the second example, you will get high amplitude because they add up together. So he basically showed, well, Newton was wrong, right? And scientists did similar thing with, and they have repeated this double slit experiment numerous times, not only for photons but also for electrons. And they basically showed that even electrons have a wave representation. So you can see, for example, on this C, subfigure C, you will see some recent measurements showing this interference pattern, definitely showing without any doubt that light or some other particles have wave interpretation. When you go to the next slide, they also did these experiments with electrons because so with photons you can do it at home, no problem. Anybody can do it with home. But with electrons, it's much more difficult because how would you generate the electrons? You need to have access to some specialized equipment, right? And the measurement is more difficult. So in the top figure, you have some kind of gun shooting shooting bullets. So these are classical. We are not dealing with electrons yet. These are some classical particles, and there are two slots, and you will get this pattern that if the bullet goes through the upper slot, then you will get this kind of Gaussian distribution, lower slots, and then when you randomly start shooting, then you will get two maxima, right? When you repeat the same experiments, not with bullets, but with water waves, you will get this interference pattern, right? So W1 here is when you use only one slot. The other slot is closed, then you use the other slot, the first one is closed, but when you combine them together, so in the first case, the first two, you will get similar Gaussian type of pattern when you compare with bullets, right? But now when you open both of them, you will get wave, definitely. With bullets, you don't see waves. Now you do this with electrons, something in between photons and bullets, right? Something in between. And you repeat this experiment, and you will get the same kind of pattern as water waves, meaning that electrons are also waves, which was very strange indeed. So let's go to the next slide. And the next slide is this where an observer come into the picture. So now, when you are sending photons, the photons will exhibit the interference pattern on the right. So on the right, this is on the right-hand side, will exhibit the interference pattern. But when you open up some detector, when you basically put now the detector at the slit, some kind of non-demolition detector, very weak detector, meaning that you know whether, because you're sending basically photons, right? And the photon can go either through the left or right slit, right? So you don't know which one. So let's say, okay, let's put a detector there, right? So we have a screen at the back, right? That's one thing. That's our final detector. But let's put additional detector just at the slot. So if you put this detector there, detecting which path this photon took, then you will destroy this interference pattern. This inference pattern, you will destroy it. So this will be like bullets, basically. So it says that the observer here, the lack of the observer on the right-hand side, or the presence of observer, makes difference between the interpretation, whether it's a wave interpretation on the right or just particle interpretation on the left. Right, so observer makes that difference, and this is where they, for the first time ever, so that's why they call it the king of experiments, Richard Feynman, the one that was leading the Manhattan Project to build atomic bomb. Right, he basically says this double slit experiments is the king of all physics experiments, basically. So for him, this was very important. So what it means, we create a meme has been created, right? If this Japanese monkey is not looking at the slot, then we have wave function, right? We have wave. If the monkey is looking at the slot, right, then we have particles.
We like that.
Yeah, so it means that the reality depends on the observer. Right, and what is observer? Observer is, physicists argue what is the observer, right? And there is a great deal of physicists that say, okay, observer is nothing but consciousness. That's the observation. Okay, but before we go that, there was a Wheeler experiment. So this was very intriguing. Lots of great scientists look into this. So John Wheeler was one of them. He was a very famous professor of physics at Princeton University. So he devised this experiment, which has been proven over and over again. It's a little bit more complex experiment. So we have a laser here. Let's look at the top right. We have a laser here, this kind of star. emitting laser. So it's emitting individual photons. Nowadays, you can emit individual photons, right? Because if you emit 10 photons, you don't know, they can go through different places. But if you emit one photon, then that photon, it's a particle, right? It basically goes, hits the beam splitter, and then the beam splitter is built in such a way that you have 50% of chances. This is truly probabilistic, right? 50% chances of being reflected, going up, red, or going through. It's basically like a glass with half covered silver, right? So imagine a mirror in which the silver is so polished that you can see through. So this is the construction. It's a very low technology, basically. It's like a aluminum or silver with a very thin thickness. So you send it, and then there are two paths. The blue path, when the photon goes through, gets reflected. So that one is a mirror. This is a true mirror, gets reflected, and then you can observe it with a vertical detector. Or when it gets reflected, the beam splitter gets reflected on the lower left. It goes through the mirror. This is a classical mirror and gets reflected. So now you have 50% chances if you put the two detectors at the top right. It has 50% of chance of observing that photon either vertically or horizontally, right? It has 50%. Now, so this makes sense, right? If you assume photons are particles. But now you do the same experiment, but at the detectors, you still have detectors, but then you put exactly the same beam splitter, right? So now the one horizontally, for example, right? Horizontally, the red one can go through or get reflected with 50% chances. And here, the wave behavior comes into play because you have two paths joining, right? And that beam splitter acts like a combiner, so it combines waves. So basically, you will only see electrons on the horizontal detector. You will not see any electrons on the vertical detector, right? Of course, you need to construct it in such a way that wavelengths, because there is a constructive addition, constructive subtraction. So you need to design it in a such way that the lengths are full wavelengths, right? So you will make this experiment. So in this case, the photon has a wave interpretation. So now he says, okay, let's say the distances are long. The light travels 1 foot per nanosecond, right? 1 foot per nanosecond, right? So if you have a few feet of distance, right, then if you observe it, at the end, you determine this is a wave function. But when you send the photon at the source, how do you know that the observation at the end that it has a beam splitter or not, that combines the two paths or not? You don't know that, right? Because there is a time separation between them. Remember, 1 nanosecond per foot. Right, so that was the question. But in order to stimulate this intrigue, he came up with more drastic interpretation of the same experiment. Let's go to the next page. So he said, okay, the source, let's say it's a quasar that emits photons. It's a quasar. Our detector is on Earth, right? And we can direct our telescope to either the upper path or lower path. And the reason there is upper and lower path is because this quasar is billions of light years away from us, right? It's not just a few feet. Each foot is 1 nanosecond, but it's thousands of light years away, right? And on the path, straight path, there is a galaxy. And the galaxy is a very heavy object, right? So according to Einstein, general relativity theory, it acts like a lens, like glasses. We have glasses, right? It acts like a lens. So basically it bends the path. So if the light goes straight through, it gets bended, basically. So that photon can go either upper path or lower path, right? And when it gets to the observer, after a few billions of years, so quasars basically emit these very regular pulses, right, at a very regular speed. These are huge objects. They send, huge amount of energy, but the distance is very large, so we observe only a few photons. Then when we direct a telescope to the upper path, we get 50% of probability observing that photon. And when we direct to the lower path, we get another 50%, right? But now, what if we put beam splitter, combine the two paths? Then we observe the same effect, basically. Exactly the same effect. So now the question is, it's much more dramatic. That question is much more dramatic. How does the quasar, when it emits a photon billions of years ago, know that in the future, billions of years after that, we will put a beam splitter or not? How does it know? Right. So that's what this is the intriguing question. So he basically said that past has no existence except as recorded in the presence, right? And universe does not exist out there independent of the act of observation. So this is a local realism, right? That it's not the question whether I take a apple out of the bag and see it is red or green, right? It's just the properties, the reality does not exist. It only gets created when we observe it.
That was a fascinating, kind of example of this effect. Just the fact that, the light basically travels or the photon as a particle or a wave, depending on the beam splitter or not being at the endpoint, and somehow
In the
it
future,
determines to do that a few billion years beforehand, or somehow retroactively, that decision gets made through the observer effect. And so just to just kind of distill all that down to why um, why does this what is the observer effect and the collapse of the wave function? Why does this serve as a rejoinder to the idea that consciousness is just an sort of a physical or an eminent quality of the brain, or an emergent quality of the brain, if it indeed does?
um, well, because if everything is just a matter, this is a materialistic view, right? Materialistic view is that everything is made of atoms or energy, right? And if consciousness is just emergent quality of that, uh, then it comes out of nothing, right? It comes out of matter and just disappears, right? But now, how do you take this and explain collapse of the wave function? Because if our brain is the observer, or if I build some elaborate detector that is an observer, I build that using atoms, right? If our mind is the brain, and brain is nothing but a very, very sophisticated collection, interaction of atoms, right, which is materialistic view, and that causes wave function collapse, then matter wave function collapses itself, right? Then anything would collapse everything. So everything will be always in the state of collapse. And this
And
doesn't happen. This
what
doesn't.
is I'm sorry, Bogdan.
Yeah, sorry. And this doesn't happen. So, for example, why in my opinion, the single reason why quantum mechanics became so popular was this Rutherford model of an atom, right? So Rutherford was the one who discovered proton, electrons, and so on. And they built this model where there is a nucleus made of protons and neutrons, right? And then there are electron revolving it, and he got inspiration from a solar system, right? That there is a sun at the center, and then Earth is moving, so electron was moving. But then somebody made a calculation, and he proposed that, right? And that makes sense because of his. It agrees with his experiments, right? He was able to detach these electrons from the atom, so it agrees with the experiment. But somebody did the calculation, and if the electron is rotating around a proton, then it will lose energy because it's a magnetic field. It creates magnetic field, and if you have acceleration, if you do on the straight path, no problem. But circular movement is acceleration. Basically, that's what the classical physics tell you. It will lose energy, so all atoms will be unstable. But we are still here, right? So definitely, that was wrong. So it means that the electrons are not particles. They are not really moving over the center, over nucleus, right? They are not really moving. They are like clouds of electrons. So they are in the state of quantumness. They are in the state of superposition, basically, right? So now, if a complicated matter, is a detector, we can call it a detector, and it can collapse the wave function, then all the atoms will collapse themselves, right? So that doesn't make any sense. So we have to bring. So Wheeler came up with another explanation that we need to have another quality which is above the physical world, above energy and atoms, which is separate from it, and that is consciousness. That get unaffected by matter. So that is a development based strictly on logic, right? Not on religion, but based on logic. That what we know up to now, how the view of the physical world is being created, it doesn't make sense that the matter will collapse itself, because it's becoming very complicated, right? We need to bring some new quality, such as consciousness, right? So consciousness is not emergent property. Consciousness actually creates matter.
So, Bogdan, this is a somewhat imperfect analogy, but it's just in terms of experiential observer effect. The Buddha talked about how dukkha, or suffering, it's suffering, it's unpleasant when it persists, and it is actually pleasant when it goes away. Pleasant feeling, sukha, is pleasant when it persists, and it's dukkha when it goes away.
Mm-hmm.
But neutral feeling is pleasant when it's known, and it's dukkha, it's unpleasant when it's not known. So you've got this observer effect, which just as soon as you bring sati or mindfulness to whatever Vedana or sensation is, it actually changes the experience of it from dukkha to sukha, or from neutral to either one of those. And I'm curious just what might be the implications of this observer effect. I mean, in Buddhism, at least in Theravada Buddhism, and it is not the same necessarily in other forms of Buddhism, but consciousness and mindfulness are not the same thing. Like, mindfulness does not exist in every moment of consciousness, but it's something which can be turned on or off. And I'm curious, what if it's possible to do any experiments, or if there have been any experiments in terms of turning on and off the observer, and if it's possible to draw implications from this, from a photoelectronic detector to human consciousness. Kind of muddled question, but what are the practical implications of this observer effect?
Yeah, so the observer, in my opinion, so not all physicists agree with this. There is maybe one third of physicists that invoke consciousness in order to explain things, but others basically, most of the physicists basically says we don't care, right? The equations work fine, right? There is a very famous saying in Copenhagen interpretation, right? The very first interpretation of quantum mechanics, which Einstein never believed in, and Schrödinger, he was also against it, right? He basically said famously, if I knew what have become of this quantum mechanics, my invention. He basically invented these Schrödinger equations. I would have never bothered with this, right? So there is still some disagreements. And the famous saying of Copenhagen school is "Shut up and calculate." The equations work fine, but we don't know how to explain it, right? Because for them, many of them are very afraid, uncomfortable, I would say, invoking consciousness, because in the Western world, consciousness or spirit uh, conjures pictures of angels. Angels, demons, Holy Ghost, God, and they don't feel very comfortable with dealing with this, right? Buddhism doesn't have that baggage, right? Consciousness is treated at a different way. So, in my understanding of quantum mechanics, is that the consciousness is primary and matter is secondary. It's not that they don't exist, right? It's primacy of consciousness. But it's not true that people say, "Oh, some Buddhist groups say that nothing exists than consciousness. Basically, consciousness is everything, right?" Actually, Vasubandhu, who was the founder, the organizer of this Yogacara school, he says objects don't exist outside of the consciousness. So he didn't say objects don't exist, but outside of the consciousness, which agrees with the modern theories of quantum mechanics, which says, okay, consciousness is primary and the matter is secondary. So it means that consciousness is primary. You mentioned the mindfulness. In my opinion, in this view, right, I haven't really spent that much time, because this is like dealing with different properties. Like, for example, quantum mechanics is the fundamental science, right? Based on quantum mechanics, we have chemistry, right? Chemistry is just very sophisticated quantum mechanics that gives another quality, right? Based on chemistry, we have biology, right? Based on biology, we have social sciences, like psychology. Based on psychology, we have finance, and so on. So there are different layers. In my understanding, I might be wrong, the consciousness is just basic layer, then mindfulness is another layer, just like a difference between quantum mechanics and biology and chemistry, right? Is just another layer. So this is just foundation. So everything is based on consciousness, and when the consciousness reaches a certain level of sophistication or maybe cleanliness, right? Cleanliness, quietness, it becomes mindfulness, right? But I don't see there is a qualitative difference in the sense as chemistry is different from quantum mechanics, right? It's just another layer of sophistication. So this is basically my understanding.
And I know you talked about Vasubandhu as the first quantum scientist, I believe.
Yeah.
But Professor, I think one thing, speaking about consciousness, and granted, we're getting to the realm of speculation here, but it kind of is interesting to explore these grounds. Longpo Sumedo will often say, it's not that the mind is in the body; it's that the body is in the mind. And you talk about the idea of the world and the wave functions that constitute quanta and those objects before the observer effects collapses them. As you talk about this as almost pure consciousness or something like that. I'm just curious, like what do you conceive of in terms of that relation between consciousness before it interacts with the wave function, and yeah, just speak to that statement a bit.
Well, you use the term pure consciousness. I don't think this is the case. That will be Advaita Vedanta, right?
Hmm.
The purest form of Hinduism nowadays, Advaita Vedanta, which, in my opinion, based on what I read, actually stemmed from Buddhism. Shankara was actually inspired by Buddha, right? So you might say another form of Buddhism, right? But pure consciousness does not exist, in my opinion, right? In Buddhism, there is always consciousness of something, right? I'm conscious of something. I'm not just conscious of consciousness. I'm conscious of something, right? So when I go to the state of mindfulness, I'm conscious of being conscious, for example, right? So animals are conscious, definitely, right? There is no doubt about it. They are conscious, and some of them are quite smart, right? But I doubt that the animals are conscious of their consciousness, are aware of their awareness. I think it's humans can only be aware of the awareness. And when I look at our lives, we are conscious pretty much all the time, but we are not aware of our awareness, right? I would say in the 24-hour day, we might be aware of our awareness of what, maybe 1 minute per day, something like that, that we are aware, maybe even less, right? For some people, maybe only 1 second or even less. The more you practice meditation, the more you're aware of your awareness. So you're aware of your awareness more and more, to the point that it becomes pretty much predominant mode of your thinking, right? You're aware of your awareness. So how does it relate to quantum mechanics? Well, in quantum mechanics, there is this consciousness, but there is always consciousness of something, consciousness of observation, right? It's like we don't subscribe to Advaita Vedanta, that there is a pure form of consciousness. There is a consciousness of something. And when there is this wave function collapse, or apparent wave function collapse, because we don't really know whether this is happening or not, right? Because Schrodinger equations don't actually show this. They don't have anything to do with wave function collapse. That's why Schrodinger never subscribed to it, right? But if we take that interpretation of wave function collapse, then we are collapsing of something going on, right? So there is a consciousness of something, right? And that is, I would say, in a very good agreement with Buddhism.
Hmm. Bogdan, I'm curious, just moving to cosmology. Um, in Buddhism, there are talk of other realms. There are heaven realms, there are hell realms, there are ghost realms. And when one starts to study quantum mechanics, quantum physics, the whole quantum realm, does it make it less easy to dismiss the possibility of heaven and hell realms and other realms that we can't see? Just curious how you yourself might conceive of that, or just how knowing these things just might shake up our certainty that there's nothing after death, or that there are nothing else than we can see. So.
Well, remember when the Soviets sent the Sputnik to the outer space, right? They Khrushchev, I think it was at the time. Somebody in the Politburo said, "We went into the outer space, into the heavens, and we didn't see any God." Right? So they say materialism, science. They call it scientific materialism. Materialism, therefore, has been proven, right? Proven. From our perspective nowadays, from the physics perspective, that is a very kind of childish, ridiculous kind of statement, right? Because there are numerous worlds. Like, for example, there is a world of quarks. We can go down into the quarks, right? We can go to the astronomical levels, right? So we simply don't know what is ever a level of quarks, right? With our minds being tied to this macroscopic level, meaning them from millimeters to millimeter size, right? We don't know if there are two quarks or two atoms fighting with each other, or two strings, in the string theory fighting with each other. We have no way of knowing that, right? So there could be a realm. I'm making the little bit ridiculous example, right, of a realm of quarks fighting with each other, but there are no instruments for us to be part of this fight and try to be an arbiter in the quarrel, right? So it's a little bit humorous example, but with so many dimensions. So, for example, string theory says that there are many dimensions, right? The concept, the recent developments in investigating time from quantum mechanics basically says that time is an emergent property, is just projection of it's emergent when we are projecting 5 dimensions into 4 dimensions, where we have we have 3 spatial dimensions plus 1 time, right? Because Einstein say temporal, spatial temporal, right, dimensions. So he said time cannot be taken separately from space, right? And space cannot be taken separately from time because the pure space doesn't exist. We always have these particle, antiparticles, virtual particles popping up, right? And they say this is the reason, most likely reason why there was a Big Bang, right? Because of this fluctuation in the time space fabric, right? So that's basically says. So from somebody who studied physics with so many dimensions, it would seem almost impossible that there will be no other realms, right? We can almost bet that there are going to be other realms, but we simply don't have instruments to go to the other realms, right? We have, for example, no way of looking what is in another galaxy, which is more than 40 billion years from us, and expanding at the speed faster than light. So there might not be connection. But if everything is made of mind, right? If mind creates all this matter, then it doesn't mean that our stream of consciousness can go into these other realms, right? We might not be able to go to these other realms with our current body because we need to satisfy the laws of physics, but our mind doesn't have that restriction, because it's beyond, as physics experiment says, it's beyond the wave function collapse, and this is what causing wave function collapse. And wave function collapse apparent is what creates this universe as we perceive it, right? So mind doesn't have that restriction.
There's a fascinating, just you bringing up quarks battling one another. There's kind of a fascinating sutta, Samyutta Nikaya 56.41, about speculation about the world. And in that we have this guy who goes to a lotus pond and he sees this fourfold army of angels come out of a lotus stalk, followed by some, asura army. And then they go back and disappear. And he thinks he's insane. And then he goes to the Buddha, and the Buddha says, actually, that's true. And don't think about that. Just focus on the Four Noble Truths.
Yeah.
I really love this way. Can we keep you on just for a little bit longer, Bogdan?
Sure.
I know you'll have to go quite soon, but one thing
No,
I'm curious is
a bit longer.
okay. Well, I'm curious. Like, do you see the paradigm as people confront this kind of real big question of the collapse of the wave function, of the observer effect, of quantum? Do you see the kind of dominant paradigm among scientists shifting at all, and in academia? Like, is there more openness to consciousness being a primary element in the universe, or is a scientific materialism still reigning strong? Do you see any shift in people who have to encounter this question?
So as I mentioned, most physicists don't care, because the Schrödinger equations, simulations, building using these equations to build something useful, right? It is estimated that 1/3 of U.S. economy is based on quantum mechanics, right? One way or directly or indirectly. They are very busy, and most of them simply don't care, right? That's why we have this motto: "Shut up and calculate," because calculations do work. There is no problem. We just simply have difficulty explaining it, and there are many theories. One of them is Wheeler's interpretation of multiverses, which basically says wave function never collapses. Right, so he wrote his famous PhD thesis where he says, okay, wave function collapse is just an illusion, because at that time of the collapse, the world splits into two, the universe splits into two, right? And in one universe, there is a resolution, let's say, spin up, and another one is spin down, right? But it never collapses, and these two worlds separate from each other, and they can never communicate, right? Except for quantum computing, right? So the reason I started dealing with this is because I started a company in quantum computing. We have some some prototypes which we are kind of getting ready for sale, in which the power, nobody can really explain the power of quantum computer, why it is so powerful. It can do calculations which are trillions, gazillions times faster than all the computing power in existence right now. The leading explanation by David Deutsch, which is a modern father of modern quantum computing, is that there are multiverses, so the world splits into multiple versions, right? And it becomes, after some time, these multiverses become inconnectable. They separate too far, but at a short period, they still can communicate with each other. And during that time, they communicate the solutions. So the reason quantum computing works is that I'm employing the power of millions, billions of universes to answer, to help my universe, to help me in this universe, to get the answer, right? So this is how it works, but it hasn't been proven yet, right? This is a good theory that many physicists believe. You asked the question about materialism. So with the materialism that matter creates consciousness, is used to be a dominant explanation. Obviously, scientific materialism was the foundation of communism, right? We know how it all ended up. Now, there is a issue of consciousness, so-called qualia, right? And the problem with consciousness and materialism is that how do you define consciousness? And there are many definitions of consciousness, right? Some people say it's the process that is going in the brain. Um, so there was this researcher, David Chalmers, who basically says, okay, the reason we are in such a big mess, we cannot decide whether it's all, whether mind is primary or matter is primary, is because we don't define consciousness properly. So he said, let's use definition of consciousness as qualia, right, as subjective experience. So how is it like, how does it feel to see blue color, or how does it feel to taste sweet? It's not the process that is going on in our brain, getting from the objects, but this vedana, this how does it feel, this new quality, how does it feel? This is the consciousness. So he basically spent decades of his professional life, scientific life, trying to convince others to define consciousness. And he said the consciousness definition is so difficult that this is a hard problem of science, hard problem. And he defined easy problem as sending man to Mars, for example, or finding cure for cancer. These are easy problems because, if we had enough money, right, we can do that. If we had money, we can follow the scientific process. But here, there is no way we can follow the scientific process and discover what is qualia, right? So he started this movement trying to define qualia. And he said famously, most likely it will take 50 years or 100 years before we really define it. Or maybe we'll never be able to define what is qualia, what is consciousness. So there is quite a bit of work going on in there, right? And I think my reason is because if mind is the foundation, creates everything, right? Consciousness creates everything, then how does it measure itself? How does fish know that it is living in water? Right, the same thing. It's part of you, part of your universe. This is what you are. So how do you define it? It's much easier to define matter because you're not matter, right? You're not objects, right? So how do you do it? So this is the problem. So lots of scientists are now working on how to define this qualia.
Professor, the Buddha did talk about the Achinteya issues where if one thought about him too much, their head would explode. And certainly, some of these discussions can brush into the realm of what can't be known or maybe isn't profitable to go spend our whole lives on. And yet, I think what you do in terms of deconstructing the solidity of view that most of us have, and just pointing to these other pathways and parallels is genuinely really fascinating to me. And just thank you for joining us, for the work you're doing, and for actually being someone who can with an expert eye bridge these two worlds for others.
Okay, thanks again for inviting me. It was a great discussion. Thank you.
Thank you.